Carbon is the cornerstone of life on Earth. It forms the basis of all organic chemistry, from simple molecules to complex structures. Carbon's versatility makes it unique and indispensable in both nature and industry. The food we eat, the clothes we wear, and even the air we breathe contain carbon compounds. Our bodies are built from carbon-based molecules. Carbon's ability to form stable bonds with many elements, including itself, is key to its importance. This bonding ability leads to a vast array of compounds with different properties and uses. Carbon compounds range from simple gases like methane to complex polymers like DNA. From developing new materials to creating sustainable fuels, the study of carbon is at the heart of many technological advancements. This essay will delve into the fascinating world of carbon and its compounds. Carbon atoms form covalent bonds by sharing electrons. Each carbon atom can form 4 covalent bonds, leading to a variety of molecular shapes and sizes. This ability to form multiple bonds makes carbon incredibly versatile. Covalent bonds in carbon can be single, double, or triple. For example, ethene, C2H4, has a double bond, while ethine, C2H2, has a triple bond. The strength and stability of covalent bonds in carbon are due to the sharing of electrons between atoms. This stability is one reason why carbon compounds are so abundant and diverse. Covalent bonding allows for the formation of complex molecules with intricate three-dimensional structures. Understanding covalent bonding in carbon is crucial for studying organic chemistry and biochemistry. Carbon exists in several different forms known as allotropes. The most well-known allotropes of carbon are diamond, graphite, and graphene. Diamond is the hardest natural substance and has a high refractive index, making it valuable in jewelry and cutting tools. In diamond, each carbon atom is tetrahedrally bonded to 4 other carbon atoms, creating a strong and rigid structure. Graphite, another common allotrope, has layers of hexagonal rings that can slide over each other, making it an excellent lubricant and conductor of electricity. Graphene, a single layer of carbon atoms arranged in a hexagonal lattice, is incredibly strong, lightweight, and an excellent conductor of electricity. It has potential applications in electronics, materials, science, and nanotechnology. These allotropes show how the same element, carbon, can form materials with vastly different properties. The study of carbon allotropes is important for materials, science, and nanotechnology. This leads to the development of new and innovative applications. Carbon's versatility is due to its ability to form a wide range of compounds. Carbon can form stable bonds with many elements, including hydrogen, oxygen, nitrogen, and sulfur. One of the most remarkable aspects of carbon is its ability to form long chains. These chains can be straight, branched, or even form rings. This property is the basis for the vast diversity of organic compounds. Carbon's ability to form multiple bonds also contributes to its versatility. Double and triple bonds introduce new dimensions to molecular structures and reactivity. Carbon forms the backbone of biological macromolecules, such as proteins, nucleic acids, carbohydrates, and lipids. These macromolecules are essential for life and participate in countless biochemical reactions. Understanding the versatile nature of carbon is crucial for many scientific fields. Organic compounds are primarily made up of carbon and hydrogen atoms. These compounds can be classified into 2 main categories: saturated and unsaturated. Saturated compounds have single bonds between carbon atoms, making them relatively stable and less reactive. Alkanes are a common example of saturated hydrocarbons. Unsaturated compounds contain 1 or more double or triple bonds between carbon atoms, making them more reactive. Alkenes and alkynes are examples of unsaturated hydrocarbons. The presence of double or triple bonds in unsaturated compounds leads to different chemical properties. Unsaturated compounds can participate in addition reactions essential for many chemical processes. Understanding the difference between saturated and unsaturated compounds is important for organic chemistry. These classifications help predict the reactivity and properties of different organic molecules. Carbon's ability to form chains, branches, and rings is a key factor in the diversity of organic compounds. Straight chains are the simplest form of carbon compounds. Alkanes, alkenes, and alkynes can all form straight chain compounds. Branching occurs when a carbon chain has one or more side chains attached to it. These branches can significantly affect the properties of the molecule. For example, branched hydrocarbons often have lower boiling points than their straight chain counterparts. Rings are another important structural feature of carbon compounds. Carbon atoms can form closed loops, creating cyclic compounds. Ring structures are common in many biological molecules, including hormones and vitamins. This structural diversity is essential for the wide variety of organic molecules found in nature and synthesized in the laboratory. The "will you be my friend" concept is a metaphor used to explain the bonding behavior of carbon atoms in organic chemistry. It highlights carbon's ability to form stable and diverse bonds with other atoms. In this concept, carbon atoms are viewed as social elements that like to form bonds with other atoms. Each carbon atom can form 4 covalent bonds, symbolizing its willingness to befriend other atoms. Carbon's friendship with hydrogen is the basis for hydrocarbons, the simplest organic compounds. The addition of other friends, such as oxygen, nitrogen, and sulfur, leads to more complex molecules with diverse functions. This versatility is essential for the diversity of organic chemistry and the complexity of biological systems. Understanding the "will you be my friend" concept helps simplify the complexity of organic chemistry. It provides a relatable way to grasp the diversity and bonding behavior of carbon atoms. A homologous series is a group of organic compounds with a similar structure and chemical properties. Each member of the series differs from the next by a specific number of atoms, usually a CH2 group. This systematic variation in structure leads to predictable changes in physical and chemical properties. Alkanes, alkenes, and alkynes are examples of homologous series. The nomenclature of carbon compounds follows specific rules set by the International Union of Pure and Applied Chemistry, or IUPAC. These rules ensure a systematic and consistent way to name organic compounds. The name of a compound provides information about its structure, such as the length of the carbon chain, the presence of branches, and the type of bonds. For example, in naming alkanes, the longest continuous carbon chain is identified, and the compound is named based on the number of carbon atoms in that chain. Understanding homologous series and nomenclature is crucial for studying organic chemistry. It provides a systematic way to classify and name compounds, making it easier to predict their properties and reactivity. Carbon compounds exhibit a variety of chemical properties, including combustion, oxidation, addition, and substitution reactions. Combustion is a reaction with oxygen that produces heat and light. Hydrocarbons, when burned, produce carbon dioxide, water, and energy. Oxidation involves the loss of electrons or an increase in oxidation state. In organic chemistry, oxidation often refers to the addition of oxygen or the removal of hydrogen. Addition reactions occur in unsaturated compounds, where atoms are added to the multiple bonds. For example, hydrogenation of alkanes involves adding hydrogen to convert double bonds to single bonds. Substitution reactions involve replacing one atom or group of atoms with another. Understanding these chemical properties is essential for the synthesis and application of carbon compounds. These reactions are the basis for many industrial processes and the development of new materials. Coal and petroleum are fossil fuels formed from the remains of ancient plants and animals. These fuels are composed primarily of carbon and hydrocarbons. Their formation involves complex geological processes over millions of years. Coal is formed from the remains of plants that lived in swampy forests millions of years ago. As these plants died, they were buried under layers of sediment. Over time, heat and pressure transformed the plant material into coal. Petroleum, or crude oil, is formed from the remains of marine organisms. These organisms settled on the seafloor and were buried by layers of sediment. Over millions of years, heat and pressure converted the organic material into crude oil. Understanding the formation of coal and petroleum is important for energy production and environmental science. Ethanol and ethanoic acid are two important carbon compounds with various applications. Ethanol is a simple alcohol, while ethanoic acid is a carboxylic acid. Both have significant roles in industry, medicine, and everyday life. Ethanol, C2H5OH, is a colorless volatile liquid with a characteristic odor. It is commonly used as a solvent, antiseptic, and fuel. Ethanol is also the active ingredient in alcoholic beverages. Ethanoic acid, CH3CoO, also known as acetic acid, is a colorless liquid with a pungent smell. It is the main component of vinegar and is used in the production of various chemicals. Ethanoic acid is produced by the oxidation of ethanol or through the bacterial fermentation of ethanol. Understanding the properties and reactions of ethanol and ethanoic acid is essential for many scientific and industrial applications.